Hello everyone, myself Faizan Beigh. So we already saw what professor and other guys talked about some technology in which you require complexity is very high for printing this. In they also they are depending upon the ink. They require some sort of ink to purchase so that they can print something. But in our case, we don't need anything. We are just producing ink from the same substrate that we are using. So the title of the my already presentation has been told by sir, and this will be the flow of my presentation. First, we will see what is graphene, why graphene is so important. That was also discussed in the session, and then we will see what are the various methods by which we can create graphene, and what is laser-induced graphene, why it's so important for us, and then we will see some literature reviews that some people have done, and what are the research gaps that we can just try to complete them. And there are some optimized parameters that I was going to discuss, which will be able to us for to create some better graphenes. So if we look at graphene, actually graphene is basically a single atomic layer of graphite. And if you look at its discovery, it was done in 2004. And from that day, people began to use graphene for lots of applications. And it was used for making a piezoresistive sensor or making a touch sensor or any other application we can target. But this was only possible when we came to know about its properties, that it has high tensile strength, it has highly conductive. All these things make graphene so wonderful that people call it a miracle material as well. And if we look at the way that people are creating this graphene, there are various methods like liquid phase method, mechanical phase method, or you can go for chemical vapor deposition. But all these methods have one issue, that either they are complex or you require some sort of technology that can be very cost effective, that is not cost effective for us. For example, you go with this chemical vapor deposition, you require a particular chamber, you require to raise the temperature, and you require a particular gases that are carbon rich. So what is the solution, and how can we move forward with some simple way of creating the similar thing? So one of the things that in 2014, professor from Rice University, they discovered that when a polyimide hits with a laser, they absorb this energy, and there is a conversion of sp3 hybridization to sp2 hybridization with the release of some volatile gases that make it a porous graphene that we usually get. So if we look what people have already done, there are various works they have tried to do, like aromatic fabrics were used to create LIG heaters. These aromatic fabrics were used because they contain some carbon, highly carbon content. So upon laser hitting, you can create some sort of sensors over them that are graphitic in nature. And if you look their thermal response, that is very poor. And for a high voltage, you require it in order to raise some temperature. But if you look at other application like they are trying to create, here their ID by IG is very less compared to what it should be, because it signifies the defect in a graphene. So it should be less as it possible. And here they try to create some micro pattern LIGs. And here we can see that they have used a complex process in order to create a same thing that we can create with a much simpler method. And one of the, I think, person is already here, Luca. He has done some work in IEEE flexible electronics. He had also created multiple of substrates on a single same settings using. And here he also has shown some LIG application. In other way, like gas sensors, people try to create gas sensors, but they didn't saw the effect of substrate itself. Whether what will be the effect of CMUT on which this material has been created, and this has shown their response is very low, which should not be in industrial applications. So what is the solution is that we can only go with some optimizing parameters. So this is the machine that we have used in order to create the same set of laser-induced graphene. This machine was not actually meant to create these things. It was meant to cut the acrylic sheets. But what we did, we optimized the same settings and tried to figure out what the same like Luga is trying to do. This machine costs us 1 lakh rupees, and if you compare with the traditional machine that people are using, it can cost you 1 crore to 75 crore. It can 75 lakh to 1 crore. It's very high cost. And if some industry, if some college or university try to figure out want to make the same thing, what they can just follow this optimized approach. So what we have seen in a research gap is there is no unified optimizing approach. Someone use some different set of laser power, someone use some different set of these DPIs or other tools. So what we are trying to do, we want to quantify all those things and want to tunable application based upon our parameters. So these are the parameters that we'll see throughout. So why we are doing this? If you look at this first application, which first sensor that we fabricated, for this we needed a clean room. So clean room needs some stuff that you require. You require a photoresist, you require metal deposition. All these things are multi-step. So what we could have done with a single step, same thing what we did here. We just do this with the laser induced graphene. So what we have followed. So first was the effect of laser. We wanted to identify the parameter. So what we saw that when a laser at a particular power and a particular speed, you only get this graphenitic nature of a carbon. But if you try to increase the power very high and you kept speed constant, then you will see that actually the graphenitic carbon is not forming, but it's getting burned out. So there is some threshold that need to be passed in order to get to those. So what we have figured out from this thing is good patterns are related to good conductivity. And if you look at this after this, the second thing was why the things are getting burned and why other things are not getting burned. So to figure out that thing, we came up with look into the DPI, that is dot per inch. So what we found that if you have to make a high quality image, you will look for always high DPI, but it's a laser, it's a high amount of energy. So the distance between two spots need to be quantified. So what we found that if you go with a lower DPI, so the connectivity will be less, so conductivity will be very small. If you go with a high, very high DPI, then the burnout will happen. So with 250 DPI, what we figure out is that only our resistance was 269 ohms, and with 350 DPI it was in mega ohm. But so if we control this gap, this G, if we control this gap distance between this, we can control the actually the resistance. So we can see here as well how the resistance is actually changing. So this is the overall area distance that we can calculate, and using this, you have to control this in order to have some highly conductive as well as it should not have distance. So second thing is effect of depth. So now the height at which the laser is hitting. So that need also be controlled. So what we found that we designed a customized scale from 1 mm to 9 mm, and what we saw that with the 6 mm height, you are getting best focal spot. That is your laser spot distance will be smaller, and your IDU-LG ratio will be also better when you compare it with this Raman effect. So also the resistance was less, but when you follow, you go with beyond 6 mm, what we saw that now the laser is not able to etch the material itself. So there is a less power, so the graphitic carbon will not happen. So after optimizing speed, power, and DPI, that is 256, then next step was to was a person who will have a laser power that will be not same. For instance, I have a 100 watt of laser. Might someone have 50 watt of laser? What should that guy do? So what that guy can do, he can control DPI and scan speed. If even if his power is less, what he can control this ratio, and he can see in which region he has to remain. If he remains in 40 to 60 joules per centimeters per region, so the graphitic carbon that will be highly conductive, and so he can follow this thing. And what also we found is that if your power is very small, then the carbon content is less. So the conductivity is also less in that case. As soon you increase power to the optimal point, that is 20% power. In my case, when I was using 100 watt of laser, so that time my carbon content was coming to almost 96%. And same thing we tried with what are the effect of support. Now, even if you are using polyimide, now below polyimide, if you have acrylic, that's a glass. That laser is nothing but it is a power that is a high temperature. So if that acrylic is not able to transfer the energy downwards to the environment, what will happen? You will get this type of reaction. So what we did, we put some metals below because metals are good, this conductor of heat as well. So what we found that with the aluminum base, our conductivity further improves, which was initially less, and our IDG-IG ratio starts improving. It becomes too close to the what naturally we can get from the graphite carbon that we can get from the market as well. So commercially, what we have seen, same thing we saw. And when we tried with this bending application at our optimal parameters at 20% with metal base, our bending was higher compared to the one with not having the metal base below. And also with this metal base, what we could have done, we can make smaller our sensors. We can also make bigger sensors as well. That can also be used for a conducting application as well. So so these are some measurement setups that we follow in order to test its mechanical strength. What we saw that Our more metal compared to one which was fabricated on the acrylic base. And also you can look at this. There are two same designs, same voltage is given to both, but the temperature rises faster in case of this one, because we have controlled the resistance here, and this resistance control is depending upon the laser parameters that we are controlling. And we also tested bending performance, that was also quite nice enough. And this is the FLR camera setup that we are using. Using this, we can just measure these results at what temperature, at what voltage, how much the temperature is increasing. That data we secure using this setup. And we also saw that for one of the design, our temperature was getting rise above this conformation of this instrument. That was, it was meant only to measure up to the 201 Celsius. So we wanted to test this material whether it will work beyond 201 Celsius or not. So what we did TGA test, thermal gradient test, and there we found that our laser induced graphene is stable up to 800 degree as well, and it does not lose its nature. And the bending results also signify the same thing. Now, why we are interested in this R? This resistance R we can control these applications. If you want 40 to 50 degree, so what you can do, you can have your laser parameters will be specified like that way. So these are some material characterization as well we did. Yes. So we can see here the this optimized LIGs, carbon content 96%, nitrogen is less, and also oxygen is less compared with the pristine PI that we already have. It had only 72% carbon. So rise in carbon is actually to the work that we already discussed it. And these are some intensity. You can see pristine was having 25K, while comparing with optimized, it was above 50K. And also, I can conclude the presentation with this, that this thing we fabricated initially with metal deposition, the same response, maybe close to the response which was coming with the LIG graphene as well. And this is a transfer, we transferred it to the PDMS and there was no issue. And what is next up will be that we can go with the green LIG as well, because they also contain carbon. So we can print directly on the leaves, bark, anything that contains the carbon. He is my professor and this is my lab mates. I would like to thank everyone for listening to my presentation. And if you have any query, you may ask me. Okay.